Okay, Year 12, Lesson 4 for vectors. This lesson is on the dot product. So this is what we've learnt so far. We've looked at geometric representation and operations, the magnitude and direction of a vector, algebraic representation and operations, and parallelism. There are two methods for multiplying vectors by one another. There's the dot product, which is what we're going to cover today. It's also called the scalar product because the answer is a scalar. And then there's the cross product, also called the vector product because the answer is a vector. Now we're not going to cover this one in this course. So the dot product or scalar product is obtained when multiplying a vector by another vector. It's called the scalar product because the result is a scalar. It's called the dot product because that's its notation. Now here's the formula. If u is equal to u1, u2, and v is equal to v1, v2, then u dot v is u1, v1, so multiply the horizontal components together, plus u2, v2, multiply the vertical components together. So let's find the dot product for these vectors p and q. So it's just going to be 1 times 5 plus 3 times negative 1. So it's really easy, isn't it? The dot product is equal to 2. But what does that mean? Now, one of the best ways I've heard it explained is that the dot product compares like components to find out how similar two vectors are. So let's just consider the base unit vectors I and j. They of course represent unit vectors in the easterly and northerly directions respectively. And let's just draw that quickly. So here we've got I and here we have j. Now how much in common do those vectors have? And what I'm talking about here is their components. How similar is 1 and 0? And how similar is 0 and 1? They actually have nothing in common at all. This one is purely east, nothing at all north, and this one is purely north. So not surprisingly, when I do the dot product, I get 0. Now let's consider a unit vector in the northeasterly direction. So we have vector A, which has components 1 on root 2 and 1 on root 2. Now, vectors I and A do have some similarity. If we draw them, here's I, here, and there is A. So we can see that this particular component here has some commonality. There's nothing with this component. So when we do the dot product, we do end up with a non-zero answer. But where we really use the dot product is to find the angle between two vectors. Now I'm going to prove this to you. So we'll consider the vectors u and v. I'm going to translate v so that both the vectors begin at the same point. And completing that triangle there, this is the vector v minus u. Now before we continue with the proof, we need to go through a couple of algebraic properties of the dot product. So we have the following relationships. U dot v is the same as v dot u. Order is not important. Here's a really important one. U dot u is equal to magnitude of u all squared. And I encourage you to prove that one. Let u be the vector x, y, or something like that, and show that left-hand side equals right-hand side. We can expand brackets. So u dot v plus w in brackets is the same as u dot v plus u dot w. And we can even do FOIL. So here we have got u dot x plus u dot y plus v dot x plus v dot y. So let's continue with our proof. By the cosine rule, the magnitude of v minus u all squared, because that's the length of that vector, will equal the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v cos theta. Now that second algebraic property said that I can write this as v minus u dot v minus u. And we can expand this out just using FOIL. This is v dot v, take away u dot v, take away u dot v, plus u dot u. I have joined those middle terms together. Now v dot v is the same as the magnitude of v all squared, and u dot u is the same as the magnitude of u all squared. And look, these cancel out. Can you see that? So we're left with negative 2 u dot v is equal to negative 2 magnitude of u times the magnitude of v cos theta. And dividing by negative 2, we have our formula. U dot v is equal to magnitude of u times the magnitude of v cos theta. And so the angle between two vectors u and v is found either by using this formula here that we just proved, or we can turn it around and make cos theta the subject. Now the angle is always taken between 0 and 180 degrees rather than using a negative or a reflex angle, but that is actually common sense. You won't have any trouble with that. Let's try an example. Find the angle between the vectors I take away 2j and 3i plus 2j. So here's our formula. On top, we want the dot product. That's going to be 1 times 3 plus negative 2 times 2. And on the bottom, we want the magnitude of u. That's the square root of 1 squared plus negative 2 all squared. And the magnitude of v, which is the square root of 3 squared plus 2 squared. And in the calculator, that gives us negative 0.124. All we want to do now is inverse cos of this number. And so the angle between the vectors is 97.1 degrees. And you can see how this has been given as an obtuse angle without us even having to do anything. The calculator will naturally sort out whether it is acute or obtuse. Now we have some geometric properties of the dot product. The first one, if the dot product is equal to 0, then the vectors u and v are perpendicular, and we also call that orthogonal. Here's the proof. If two lines are perpendicular, then the angle between them is 90 degrees. So using our formula, u dot v is equal to magnitude of u times the magnitude of v cos 90. Cos 90 is 0, and so therefore the dot product is equal to 0. Here's an example. The vectors a and b are perpendicular to each other. Find the value of k. So we want to work out the dot product and put that equal to 0. So we do 4 lots of k plus 3 in brackets plus 2 lots of k and put that equal to 0. And just solving it, it's a very simple equation. 4k plus 12 plus 2k is equal to 0. Collecting like terms, 6k is equal to negative 12. K must be equal to negative 2. And here's our second geometric property. If the absolute value of the dot product is equal to the magnitude of u times the magnitude of v, then u and v are parallel vectors. Now, this is a really good example of how these signs here kind of mean the same thing, but in this case this is the absolute value, and in this case it's the magnitude. Okay, because u dot v is a scalar. So all we're doing is stripping the negative off here, but in this case we're working out the length of the vector. So let's prove this. If two lines are parallel, the angle between them is either 0 or 180 degrees. So here's our formula. U dot v is equal to magnitude of u times the magnitude of v cos 0. Cos 0 is 1, so that gives me magnitude of u times the magnitude of v. Or it could be 180 degrees. And cos of 180 is negative 1. So you can see how the dot product is equal to positive magnitude of u times the magnitude of v, or negative magnitude of u, magnitude of v. And that's, of course, the definition for the absolute value. So therefore, the absolute value of u dot v is equal to the magnitude of u times the magnitude of v. And here's an example. Suppose u and v are parallel and their lengths are 4 and 5 respectively. What are the possible values of the dot product? Okay, because they're parallel, we know this. Okay, the absolute value of u dot v is equal to the magnitude of u times the magnitude of v. We know these. The magnitude of u is 4, magnitude of v is 5, and 4 times 5 is 20. So what could this be? This could be positive 20 or negative 20. And there's our answer. Now we haven't quite finished with vectors yet, but this is what you're given on the reference sheet. So we're given magnitude of u, which is the square root of x squared plus y squared. the formula that we've just been working with, and we're also told the dot product is equal to x1, x2 plus y1, y2, and we're given the vector equation of a line, which we haven't covered yet. Okay, next lesson is on projections.